Okay, so we're going to start our unit on systems of equations. We are going to look at linear and quadratic systems and quadratic systems. If you recall from last year, you also did a unit on systems of equations, but you were only looking at linear and linear, so we're going to build on that this year. So for our first section, we're going to be looking at solving systems of equations graphically, and we'll be looking at graphing them manually as well as on our graphing calculators. And if you recall from last year, when you solve a system of equations, what you're looking for are the points of intersections between your lines. So any ordered pair xy that satisfies both equations in a linear system, in a system of linear quadratic or quadratic equations is a solution of the system. So for example, the points 2, 4 and negative 1, 1 are solutions of the system y equals x plus 2 and y equals x squared. So I have them graphed over here on the side. So the red graph is your quadratic, so y equals x squared, and your blue graph is your linear equation, so y equals x plus 2. And the points 2, 4 and negative 1, 1 are solutions because that's where the two lines intersect. Okay? So the ordered pairs 2, 4 and negative 1, 1 satisfy both equations. So if we want to show algebraically that they are indeed solutions of the system, then what we want to do is to plug those values back into the original equations and show that the left side and the right side are equal. Okay, so let's test the point 2, 4, and we will start by substituting into our linear equation. So 4 for y and 2 for x, so 4 is equal to 4, so that works. And we will plug it into our quadratic. So 4 is equal to 2 squared, so 4 equals 4, so that works too. So let's test our second point, negative 1 and 1. So we'll plug that into our linear equation. We get that 1 is equal to 1, so that works. And then into our quadratic. And 1 equals 1, and that works. Okay, so the points 2 and 4 and negative 1 and 1 are solutions to the system y equals x plus 2 and y equals x squared. Okay, so let's take a look at what solutions of linear and linear systems look like and quadratic systems look like. So a system of linear quadratic or quadratic equations may have no real solution, one real solution, or two real solutions. A quadratic system of equations may also have an infinite number of real solutions. Okay, so let's take a look at our quadratic and our linear. So no point of intersection means no solution. Okay, so what would that look like on this graph? Well, if I was to draw a line on this graph, okay, and I can draw it anywhere as long as it doesn't intersect the red line, then I have a system of equations that has no solution. One point of intersection means that we have one solution. Okay, so how would that look like if we were graphing it on this graph? Okay, well what that means is that our line is only going to touch, our blue line is only going to touch our quadratic at one point. Okay, and so this is our point of intersection. Okay, and something else for you to note, when a line touches another line at exactly only one point, okay, it's called a point of tangency. Okay, so a tangent to the curve is what we're looking at. Okay, and it's when a line touches the curve at one point. Okay, now I'm just going to give you an illustration here. So here's a line 1, and then I'll draw another line on it that looks like this. Okay, and you can see that we have 2 points of intersection. Okay, we have one here and one here. So I'll call this point D and this point E. Now our first point here, D, okay, is not a point of tangency. Okay, and that's because it goes through the black line. All right, let me name this too. I'll call it line 2. Okay, that's because at this point, line 2 goes through line 1 from top through to the bottom. Okay, or from top to bottom. So it goes right through the line. If we take a look at point E though, it just touches the line. It doesn't actually go through line 1. Okay, so we say this is a point of tangency. Okay, so if we have 2 points of intersection, that means that we have 2 solutions. So if I draw a line so that it goes through our quadratic, our parabola, at 2 points, okay, here and here, then we will have 2 solutions for this system. Okay. Now, if we go to the left of the screen, what would the graph of a system of linear quadratic equations with an infinite number of solutions look like? Okay, well, let's draw an x and y axis. I'm going to draw our parabola on here. Is there any way for you to draw a line on this grid where you would have an infinite number of solutions? Okay, if you came to the conclusion that it's not possible, then you're correct. Okay, so there's no way that that would work, so not possible. All right, so there's no way that you can have an infinite number of solutions between a quadratic and a linear equation. Okay. All right, so let's take a look at a quadratic and quadratic system. So we want to show what a system looks like when there is no solutions. Okay, in other words, that there are no points of intersection. Okay, well, there's a couple of ways you could draw the graph. Okay, one way is that you could draw a parabola that opens down and doesn't actually touch the red parabola. Okay, and the other way you could draw it is if you draw a parabola inside the red one, like this. Okay, and so the arms of the green parabola will never touch the arms of the red one. Okay, so that's a couple of ways that you could do that. Okay, how about if you want to show one solution? That means you have one point of intersection, and so that would look something like this. Okay, so you'd have your parabola meet up with the red, okay, at one point. Okay, and if you are thinking that this is a point of tangency, you are correct. Okay, it's where the curve of the blue line meets the curve of the red line at only one point. Okay. All right, and what does the system of quadratic-quadratic equations look like when you have 2 solutions? Well, you're going to have 2 points of intersection, right? So an example of that could be like this. So you have one intersection here and one here, and so you have 2 solutions. Okay, so what would the graph of a system of quadratic-quadratic equations with an infinite number of solutions look like? All right, well, let's draw our grid again. Let's draw our red parabola on the grid. Now, we want to show a system where you have an infinite number of solutions. Now, if you remember from your math last year, if you could map or graph one line on top of another, you would have an infinite number of solutions. So the same thing holds true here. if you were to graph another parabola over top of this one exactly, then you would have a system of quadratic-quadratic equations where you have an infinite number of solutions. Okay, so you want to graph one parabola on top of another. Okay, so that ends our introduction. In our first example, we're going to solve a system of linear quadratic equations graphically, and we are going to look at it manually. Okay, so not on our graphing calculators just yet. So we've been asked to solve y equals x plus 3 all squared plus 2, which is our quadratic. And y equals negative x plus 1, which is our linear equation. Okay, so let's start with our quadratic. Y is equal to x plus 3 squared plus 2. Now this is in vertex form. Okay, so we can get our vertex from that. So we'll take a look at the 3 inside the bracket, and remember you choose opposite signs, so negative 3, and then we take the number on the outside, on the right of it, and it's positive 2. We leave the sign, so our vertex is at negative 3 and 2. We notice that our quadratic is positive, A, okay, and so it opens up. And we also know that because A is equal to 1, that it is congruent to y equals x squared. Okay, so we'll start by graphing this. We will graph our vertex at negative 3 and 2. It opens up, so we're going to be graphing up this way. Because A is 1, we can use our knowledge that we have about graphing a quadratic where A is equal to 1 by going 1 to the right of the vertex, and 1 squared is 1, so we have a point here. Start at the vertex again, 2 units to the right, square 2, you get 4, go 4 units up. You go to the left, 1 unit to the left, square 1, you get 1. Start at the vertex again, 2 units to the left, square 2, you get 4, and you get this 5th point, and so you get this graph. Okay, y is equal to x plus 3 squared plus 2. Okay, so now we're going to graph our linear equation. If you notice, it is in the form of y equals mx plus b. So you can tell from the equation that your slope, which is m, is negative 1, and your y-intercept is positive 1. Okay, now remember, your slope is rise over run. Okay, so when you have a slope of negative 1, it means negative 1 over 1. Okay, so we start by first graphing the y-intercept. We have a y-intercept at 1, so we're going to plot that point. And we have a slope which is negative 1 over 1, which means you're going to go to the left 1 and up 1. Okay, so start at your y-intercept, go to the left 1, up 1, go to the left 1, up 1, left 1, up 1, and all the way up, and you can see that your line is like this. Okay, and this is y is equal to negative x plus 1. Okay, so by looking at the graph, you can see that you have 2 solutions. You have one here and one here. So the coordinates of this point are negative 5 and 6, and the coordinates of this point are negative 2 and 3. Okay, so if we go down to B, it asks us to verify our solution. So we've got 2, right? We have We have one at negative 5 and 6, and we have the second one at negative 2 and 3. Okay, so remember from the introduction, you need to show that these points satisfy both equations. Okay, so let's start with the quadratic. We're going to plug in We're going to plug in 6 for y and negative 5 for x, and we're going to simplify. So in the bracket you have negative 5 plus 3, which is negative 2. And then negative 2 squared is 4, and 4 plus 2 is 6, so you can see that that works. Okay, and then we go to our linear equation, which is y is equal to negative x plus 1, and in place of y we're going to put 6, and in place of x we're going to put negative 5. Now notice you've got a negative in front, so really what you're doing is you're going negative, and then you're going to put negative 5 in place of x. So you have minus negative 5. Okay, and remember, minus negative 5 makes that a positive 5, so you have 5 plus 1, and so 6 is equal to 6. Okay, so we'll try our second point, negative 2 and 3. Do the same thing. We're going to plug into the quadratic. Okay, in place of y, we're going to put 3. In place of x, negative 2. So we get 3 is equal to negative 2 plus 3 is 1. And so we get 1 squared is 1 plus 2, and we get that 3 is equal to 3, so that works. And then we plug that into our linear equation. So 3 for y. And remember, we're going to plug in for x. We've got this negative on the outside, so we're going to put negative and then negative 2 plus 1 minus negative 2 makes a positive 2, so we get 2 plus 1 is 3, and so that works. Okay, so this concludes our first example. Okay, so in example 2, we're going to solve a system of quadratic-quadratic equations graphically, and once again we're going to be doing this manually. And you've been asked to graph y equals x minus 4 squared minus 3, and y is equal to negative x minus 3 all squared plus 2. Okay, both of these are quadratics, so let's start with our first one. Okay, so from this graph you can see that your vertex is at 4 and negative 3. Because a is positive, it opens up. And because a is equal to 1, it is congruent to y equals x squared. Okay, meaning it has the same shape. Okay, so let's start by graphing that. We have a vertex at 4 and negative 3. It opens up. It has the same shape as y equals x squared. So 1 to the right, 1 squared is 1. 2 to the right, 2 squared is 4. So we're going to go up 4 units. So 1, 2, 3, 4. And we're going to plot another point on the right here. So we're going to go 3 units over to the right. 3 squared is 9, so 3, 6, and 9, so we have another point here. Okay, and we will do the same thing on the left of the vertex, so 1 over and 1 up, 2 over and 4 up, and 3 over and 9 up. Okay, and then we have our first quadratic. Okay, so this is y equals x minus 4 all squared minus 3. Okay, so the second quadratic is y equals negative, and then x minus 3 squared plus 2. And you can see that your vertex is at 3 and 2. Because a is negative, it opens down. And the absolute value of a, because a is negative 1, the absolute value of that is 1, so it is congruent to y equals x Alright, so let's start by graphing the vertex. It's at 3 and 2. It's going to open down. It is still congruent to y equals x squared, so we're going to move 1 to the left of the vertex, square 1, and we get 1, so we're going to move in the downward direction. 2 over to the left of the vertex, and we square that, we get 4. Okay, so we have that point, and then we'll go 3 over, square that, that gives us 9, so that's 3, 6, and 9, so we have another point right here. And then we will do the same thing to the right of the vertex, so 1 over and 1 down, 2 over and 4 down, and 3 over and 9 down. And so you get this quadratic. Okay, and this is y equals negative x minus 3 all squared plus 2. Okay, so from the graph, you can see that we have 2 points of intersection, one here and one here. Okay, so our first point here is at 2 and 1, and our second point is at 5 and negative 2. Okay, and we are going to verify. So we will plug them into our original equations. We'll start with the point 2 and 1. And we will plug that into y equals x minus 4 squared minus 3. And then into y equals negative. And then x minus 3 squared plus 2. Okay, so plug 1 in for y, 2 in for x, and simplify. 2 minus 4 is negative 2. Negative 2 squared is 4, and so you see that 1 is equal to 1, so that one works. And we will plug that into our second equation, plug 1 in for y, we're going to go negative, plug 2 in for x, minus 3 squared plus 2, 1 equals negative, and then 2 minus 3 is negative 1, we square that. Negative 1 squared is 1, but there's a negative in front, so we get negative 1 plus 2, and so we see that 1 is equal to 1, so that works. Okay, and then we take our second point, which is 5 and negative 2, and we do the same thing. Okay, so negative 2 in for y, 5 in for x. 5 minus 4 is 1, 1 squared is 1. And negative 2 equals 1 minus 3, which is negative 2, so that one works. Okay, and we plug into our next equation, so in place of y we put negative 2. And 5 in for x. We get negative 2 equals negative, and then 5 minus 3 is 2, and 2 squared is 4. And negative 4 plus 2 is negative 2, so negative 2 equals negative 2, so you know you are correct. Okay, so that ends our discussion on solving a system of quadratic and linear and quadratic equations graphically using a manual method. Okay, and so in the next video we're going to take a look at our graphing calculators. Okay, so in this video we're going to be taking a look at solving a linear quadratic equation system using our graphing calculator. Now this handout is for the TI 8384 calculator, but for those of you that have Casios, you will have the handout that is specifically for the Casio calculator. Now I'm not going to go into how to graph your quadratic and your linear functions on the graphing calculator, or how to find your intersection points in any detail. You can do the reading on your own, but I'm just going to go through the process with you, and then we will verify our answers at the end of this handout. Okay, so for those of you that have Casios, just follow along on your handout. The process is the same. Okay. So we're going to take a look at two equations, y equals 4x plus 3, which is your linear equation, and y equals 2x squared plus 8x plus 3, which is your quadratic equation. Okay, so your first step is going to be to enter these equations into your graphing calculator. Okay, so you need to go to your y equals screen and type those in. And then you are going to want to set your window settings, and for this particular graph you can see that I have your x min at -5 and your x max at 5, and your y min at -10 and your y max at 10. Okay, and then once you've graphed them in, you should get a graph that looks like this screen right here. Okay. Alright, so your next step is to actually solve. Alright, so when they ask you to calculate each intersection, that means solve the system, right? And so you need to go to your menu where you're going to find the function that allows you to find the intersection points on your graph. Okay? Alright, so then, for those of you that have the TIs, you're going to have to work that out twice, right? Okay, so the first intersection that we get is this one here, and it is at 0 and 3. Okay, and when you're solving graphically, you really should put those intersection points on the graph. Okay, and then your second point of intersection is here, and that is at -2 and -5. Okay, so you can see that this system has 2 points of intersection. Now, for those of you that have Casio calculators, you will have the same kind of diagrams, okay, with your intersection points listed on that also. Okay, all right, so the last thing that you will be expected to do outside of graphing this and sketching it is to verify that the 2 points that you have on your graphing calculator are correct, and you're going to verify algebraically. Okay, so you're going to plug, so we're going to take a look at the first point, 0, 3, okay, and you are going to start by plugging in that x is equal to 0 into y1, and so you're going to get 4 times 0 plus 3, and you get that y1 equals 3, and you would expect that, right, because the second coordinate of that point is a 3. Okay, and we'll do the same thing for y2. We're going to plug in 0 for x. Oops, hang on. And you get that y2 is equal to 3, which once again you would expect because that's the y coordinate of your point of intersection. Okay, so what is the result? The result is that in both cases y is equal to 3 when x is equal to 0. So therefore, one solution is 0 and 3. All right, so we're going to do the same thing for x equals -2 and y is -5. Okay, so the point -2 and -5. So we're going to plug in -2 for x, and that's going to give us -8 plus 3, which gives us -5, and we would expect that because that's the y coordinate of our point. And then we'll do the same thing for y2. And you get that y2 is equal to -4 minus 16. Oops, I forgot the square, sorry. -2 squared is 4 times 2 is 8. Okay, minus 16 plus 3. And you get 8 minus 16 is negative 8, and negative 8 plus 3 is negative 5. Okay, and once again, that's what you would expect. So what is the result? The result is that y is equal to negative 5 when x is equal to negative 2. So therefore, the second solution is negative 2 and negative 5. Okay, so that concludes our discussion on using your graphing calculators to solve a system of equations.